I set this up for myself, but we are going to do Unit 13 immediately after this, but I wanted to introduce what's called summation notation. And yes, calculators do this. I just want to point out, because this will make more sense with sequences and series after I do this. So this looks fancy. We call it sigma because that's the Greek letter. If you have any any knowledge with the Greek alphabet, or if you've driven by a college, university with the Greek community, and feel free to ask questions in class, but I'll just leave it as that. And we use sigma because it starts with the S. It's a Greek letter S that means summation, which means to add. Look at all these adds in here. So this looks really confusing, but it's not too bad. What you're doing is, I hope you can tell on your page that this says I equals 3. So you plug 3 in for I. And then you go to the next integer after 3, which is 4, and plug that in for I. And then you go to the next integer, which is 5, and plug that in for I. And that's when we stop. So just with a different color, I'm going to make a note that you start with 3, and you stop once you get to 5. And then from there, you add between each of those. So we're looking at 6 plus 8 plus 10, just performing the arithmetic. And that's what this notation is saying up here. It's like what you would see in a math book. And you're left with 14 plus 10, which is 24. And that's what we're going to practice with some of these. It gets a little tricky, though, because you have to think about, well, if we have -1 to square the number, what's going to happen? But again, you can see I'm starting with -1, kind of getting into the next problem, but that's okay. And we stop once we get to 3. So -1 when you square, it's +1. 2 squared is 4, 3 squared is 9, and you can just count from there that you would get 15. Hopefully my math is correct. Next one's, again, don't just assume certain things. I would encourage you to work through all of it, like 2 to the -2nd, 2 to the -1st, 2 to the 0, 2 to the 1st, and then 2 squared, because this is 1/4. 1/2, 1, 2, and 2 squared is 4. So as you count it up, 4, 5, 6, 7 and a half, 7 3/4. Or you might prefer 28, 29, 30, 31/4. As I look at the next one, this one's sort of interesting because if you take -1 to the first power and then -1 to the second power, there's going to be a pattern here. So you might come across a problem that seems like a lot, but it's probably not that bad. Because when you take something to an odd power, it's going to stay negative. This is to the even power, so it's going to be positive. And several things cancel. -1 plus 1 is 0, 0. You get an answer of -1. I mean, at some point it's just going to be repeating. You might even do a little bit of work in your head, like doing 2 times 0 in your head plus 1 is 1. 2 times 1 is 2 plus 1 is 3. And then 5 would be the last term, 5, 6, 7, 8, 9. And then again, 1 plus 1. I guess we were just having the point that you can have multiple i's. And then plug in 2. 2 plus 1 is 3. And then plug in 3 for I. 3 plus 1 is 4. So we're looking at 2 plus 6 plus 12, which I believe comes out to exactly 20. So hopefully you can build some confidence. And I will point out that the calculator will do some of these problems. So I'm going to encourage you to do this by hand first. But I'll also point out, since we've gotten used to alpha window in the previous section, there's actually another place that we use so often in math. And this is where you don't have to use I. By the way, we call it an index I, but you don't have to use that letter. You can use any letter you want. I'll just do A. So I'm hitting alpha math to do any letter I want. And your calculator will do this correctly. just anywhere that you have the I in the problem, you put an A. I guess I should have mentioned that the I in this context is not the imaginary unit. But you can see that the calculator will spit out the correct answer. And what's really going on is it's doing 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And just judging by the correct answer being 12, that must be the common denominator. So they change 1 to be 12 twelfths, 1/2 to be 6 twelfths, 1/3 to be 4 twelfths, and 1/4 to be 3 twelfths. And yeah, apparently that adds up to be 25. 12 plus 6 is 18, 22, 23, 24, 25. So I don't teach you that just to have you cheat, because, let me kind of scroll down here. In exercise 4, big deal if you have it, we want you to come up with your own formula. But there's actually an infinite number of correct answers, but there's even more wrong answers. But before I do that, I'm going to get into the next problem, where they're getting you to practice this type of problem, where you have 3 combination 0, and then x to the 3 minus 0 power would be third, and then y to the 0 power. And then go on to the next one, 3c1 x squared y to the first, plus 3c2 x to the first, y to the second, and kind of ran out of space, 3c3 x to the 0, y to the third. And if you work it out, what you'll see is that this is x cubed, because I'm not erasing, but that's going to be 1, that's going to be 1. 3x squared y, this is equal to 3 as well, xy squared. And then similarly, this is 1 and this is 1, so we're left with y cubed. And what we actually had going on here is the binomial expansion of x plus y to the third power. So trying to make that connection from the previous unit and the connection to the thing that we're going to do next. So the tricky thing with this one, and I don't want to give you too much, but sometimes you can just look at these problems and know what's happening, is you can let your index start at whatever you want. And there's a reason why I'm going to start with 3, because I'm looking at all of these numbers, and those appear like they're perfect squares to me. And you just have to think critically about this, that when I need to stop, well, think about how 3 squared gave me 9, so what number squared would give me 100? I would have to stop at I equals 10. Now, the answer is obvious once your teacher just tells you, but you don't, you could think a lot more about this. And maybe the next one I'll do a couple different ways, because I'm just looking at this and I see a pattern going on that each one of these I could just multiply by 3. And how about this? I'll show you, you don't have to use I. Well, I'll use I first. And so I'm just thinking about myself, is 3 times what would give me -6? It has to be -2. So I could do the same thing over here. 3 times what would give me 15? That answer would be 5. But I will point out that there's some other correct answers, just if you wanted to. Like, you could make your own problem that's maybe 3i minus 6. How about this? I'll use k. I think somewhere in the homework it wants you to use k, I think. It might be on the test. But you could actually start at 0, and 3 times 0 minus 6, yep, that worked there. So 3 times what minus 6 would give me 15? That answer would be 7. So there's a lot of different ways that you could come up with some of these answers. The same thing goes with the next one. I'll just use n just to show you can use whatever variable you want. Whoops, that's not how I wanted to write it, but I'll leave it that way. It's 5 to the n power, and the way I'm thinking about it is if I took 5 to the -2nd power, I would get 25 in the denominator. And then you might even need a calculator to think about it. I'll show you real quick. 5 to the -2nd power gives me that 1 over 25. You just might have to hit that fraction key. Oops. And you can see that it's going to be the same thing for the other ones as well. 5 to the negative first is 1/5. 5 to the 0 power. So when do I stop? And again, I am a math teacher, so I can do this, more or less have these answers memorized. That 5 to the 4th power is 625. But feel free to guess and check. There's some merit to guessing and checking. But you also have some multiple choice questions, and that's where guessing and checking might not be your friend. I think what I would do if I were doing these problems is do each one individually. So thinking about how 3 to the 1st power is 3, so far so good. But 3 to the 2nd power is 9. Let's stop right there. That's not the right answer. So if I did the next one, 2 to the 0 power is 1 times 3. Yep, that's 3. 2 to the 1st power is 2 times 3 is 6. So far so good. 2 to the 2nd power is 4 times 3 is 12. Yeah, this one's looking good so far. So let me just show you if the other ones are good. I hope you would disagree with this one, like 3 plus 4 all the way to 48. Yikes, not a good answer. Same thing with this one. If you plugged in 0, 6 to the negative 1st power equals 1/6. That doesn't even start out good. So I believe we would have been right if we continued on number 2. And then this next one's actually kind of a fun problem. Don't worry, don't hang up too much on these words. A series is a sum. That's another synonym that we use in math. Again, don't get hung up on these words, but practice some of these problems. And what I like about these problems is there's a pattern that goes on. That we have 1 over 1 minus 1 over 1 plus 1. All right, that's the first term. But then we go to the next term, which would be 2 minus 1 over 3. And then we go to the next term, which would be 1/3 minus, 3 plus 1 is 4. Do you see something happening here? I'll write one more. I hope you see it, that they immediately cancel each other out. So the question is, when would they stop canceling each other out? And that answer would be, let me put ... Even this 1 over 99 would cancel because we need that last term, minus 1 over 100. So hypothetically, that would cancel the next one, which this would cancel this one. So we're left with 1 over 1 minus 1 over 100, which is pretty interesting because you could then get the same denominators, 100 over 100 minus 1 over 100, which would give me an answer of 99 over 100. And that's what they mean by some interesting things, is because you don't have to do all 99 numbers and still get the answer. If you use a decimal, if you wanted to change it to a decimal, it would be 99 hundredths as well. But you should be ready for the homework now.